Thank you everybody for attending this presentation. The title of my talk is Spacetime Optics and Photonics, a new frontier for structured light. This is a very new topic that I'm involved in over the last couple of years. It's very fast moving and we're learning things as we move along. And hopefully I can infect you with some sense of excitement over what's happening in this field. So as you see from the title, we have the word space and time. In optics, studying and exploiting the spatial and temporal degrees of freedom have typically been in two separate communities. There's a community of microscopy and astronomy and optical imaging that is based on manipulating and exploiting the spatial aspect of light, focusing light to a very small spot, discerning very far away and close by objects. A separate community has focused on studying the temporal degree of freedom of light, generating very short pulses to discern events that happen at very short periods of time, or creating very high energy pulses by combining a lot of power in a very short amount of time. And I think Andy's group at Purdue is one of the leaders in the applications of pulse light in communications and other areas. These two communities have remained more or less parallel and isolated from each other in optics. What I am going to be talking about today is what are the consequences of manipulating the spatial and temporal degrees of light, not just at the same time, but jointly manipulating them and creating optical fields in which the spatial and temporal degrees of freedom are inextricably linked. The consequences of that we have found over the last couple of years is that the propagation of such fields follows very different rules in free space, and the interaction of these fields with photonic devices is quite distinct from the interaction of traditional pulsed beams with these devices. I'm going to, after introducing space-time optics, and give you a short history of this topic, how I define space-time wave packets, how we synthesize them, and then the majority of my talk are going to be about some of the recent applications and achievements that we've been able to investigate using these new forms of optical fields. In 1983, James Brittingham out at Lawrence Livermore Labs published a theoretical paper where he found a mathematical function that satisfies Maxwell's equations and represents a pulsed beam, an optical field of finite spatial and temporal extents that nevertheless propagate in free space without diffraction and dispersion. This came as a shock to the optical community. There are a couple of previous relevant results, but they were both, whether by McKinnon or Berry, were produced in the context of quantum mechanics and so went unnoticed at the time by the optics community. Brittingham's paper was the first that alerted the optics community to the fact that there may be optical field structures that propagate with unexpected characteristics. This was in the 80s, so there was the heyday of the Strategic Defense Initiative, or otherwise known as Star Wars, and the Department of Defense was quite intrigued by this and called immediately for a workshop to be held at MIT to check the mathematics of Brittingham's paper. Brittingham didn't have a derivation for his function. He admitted that he tinkered with mathematical functions until he found one that satisfied Maxwell's equations with those properties. It turns out that the mathematics was correct, but for the 80s and 90s, nobody had a clue how to synthesize such types of pulse optical fields. Subsequently, X-rays were developed in ultrasonics, and they were demonstrated in optics by Peter Sari in '97. However, the properties of these wave packets don't diverge much from the properties of traditional pulse beams, specifically the group velocity is still seen. Interestingly, in '87, as most of you know, Durnan and Eberle out in Rochester produced the Bessel beam, which is a monochromatic diffraction-free beam. And interestingly, the Bessel beam is the monochromatic limit of Brittingham's wave packet. So it's an interesting accident, probably an unfortunate accident in the history of optics, that the first diffraction-free pulse beam was developed before the first diffraction-free monochromatic beam. Obviously, it's much easier to synthesize Bessel beams, and that concept took over, and the Brittingham's paper has pretty much been forgotten by the optics community. What I want to show you today is that there is a variation of Brittingham's focused wave modes that are actually quite straightforward to synthesize and whose properties can be readily controlled in very unexpected ways. There's a review paper we published, kind of a non-technical review in OPN the other year called Weaving the Rainbow, that I recommend you read if you're interested in this topic. It gives you a non-technical overview of what we're doing. The title you probably recognize from John Keats' famous poem, where he laments the impact of optics on culture. He was commenting on Newton's prism experiments. Philosophy will clip an angel's wings, unweave a rainbow. I'd like to think that the impact of optics on culture is a bit more positive than that, and I'd like to think that what we're doing is actually weaving a rainbow. You can see in the setup why I say that. Later this year, or early next year, there'll be a big review paper in Advanced in Optics and Photonics with a more technical review of the state of the field. Now, for the majority of the talk, there's this a technical tool that would be very useful to keep in mind, and it hasn't been an important technical tool in optics, but I hope to convey today why I consider it to be crucial to understand what we're doing here. This is the concept of representation of optical fields on the surface of the light cone. The light cone is simply the cone that represents geometrically the dispersion relationship of a pulse beam in free space. If we retain only one spatial dimension, x, and ignore y, keep the field uniform in y or have it circularly symmetric, so kx is the radial wave number, but let's just assume we only have the transverse wave number, kx. Then in free space, we all know that kx squared plus kz squared is the total wave number, or omega over c all squared. Geometrically, that's represented by a cone, surface of a cone. Any monochromatic plane wave corresponds to a point on that cone. Therefore, any pulsed field, any physically realizable pulsed field, corresponds to some collection of points on the surface of the light cone. A monochromatic beam, as we have here on the left, results from the intersection of this cone with a horizontal iso frequency plane. All the spatial frequencies have the same wavelength. Hence, all monochromatic beams lie in the circle at the intersection of this horizontal plane with the surface of the light cone, whereas a traditional pulse beam, one with finite spatial and temporal extents, and therefore finite temporal and spatial bandwidths, will be represented by some two-dimensional domain on the surface of the light cone, representing the finite temporal and spatial bandwidths. Typical beams produced by ultrafast lasers have the spatial and temporal aspects independent of each other. Each wavelength, if filtered, reproduces the same beam. In other words, each wavelength is associated with all the spatial frequencies, and vice versa. Each spatial frequency comes in all the colors. So if one thinks of the spatial and temporal degrees of freedom as two axes in some spectral representation, with one axis being kx, the spatial frequencies, and the other axis, the omegas or lambdas, the temporal frequencies, then a monochromatic beam would be a single line, single frequency, but all spatial frequencies involved, whereas a traditional pulse beam with independent spatial or separable spatial and temporal degrees of freedom would come in a two-dimensional grid as we have here. Space-time wave packets are ones in which each wavelength is associated with a single spatial frequency, and vice versa. Each spatial frequency is associated with a single wavelength. So on that two-dimensional grid representing the spatial and temporal spectral degrees of freedom, I have a one-dimensional trajectory carved out, such that each color, each wavelength is associated with one spatial frequency or one spatial sinusoid, whether with increasing, with the correlation being positive, higher frequencies associated with higher spatial frequencies, or vice versa. The specific trajectories we are interested in are most readily perceived on the surface of the light cone. We are interested in pulse beams whose spatiotemporal spectra result from the intersection of the light cone with tilted planes. It's important that that plane be tilted, not horizontal, because if it's horizontal, you'd have a single color. For tilted planes, you'll have finite spatial and temporal bandwidths, so finite spatial and temporal extents, so that we have pulsed beams even though we have a one-dimensional trajectory rather than a two-dimensional patch, which is a consequence of the correlation or close association between spatial and temporal degrees of freedom. Each spatial frequency, spatial sinusoid now comes in one flavor, in only one color. Turns out that if you are able to construct optical fields and following this recipe, these pulse beams will propagate in free space and in transparent dielectrics without diffraction or dispersion. The group velocity of the wave packet is determined by the tilt angle of this plane. Therefore, one can create these pulses traveling in free space at arbitrary group velocities above or below C, superluminal or subluminal, without violating special relativity, by carving out the appropriate spatiotemporal spectrum. What I want to convince you is that this is actually readily doable in the lab, and using a setup that doesn't differ too much from Andy's well-known 4F configuration for ultrafast pulse shaping. We start off with a plane wave pulse. So we have a finite temporal spectrum but a single spatial frequency. We then spread the spectrum in space and collimate it via diffraction grating and cylindrical lens. The collimated spectrum is then incident on a two-dimensional spatial light modulator. Each wavelength now occupies a column on the spatial light modulator. Rather than give each wavelength a single phase, as typical in ultrafast pulse modulation, I give each wavelength a spatial distribution in the orthogonal direction. That is typically a linear phase with different slope, hence you can think of it as deflecting light at a slightly different angle for each wavelength according to a prescribed mathematical equation, or equivalently attaching a specific spatial frequency to each wavelength. The retroreflected field passes back through the lens to the grating. The grating superposes the wavelengths on top of each other again, thereby constituting the pulse, which in this case is now a space-time wave packet because each wavelength is associated with a prescribed spatial frequency. By changing the phase pattern on the spatial light, this two-dimensional phase pattern on the spatial light modulator, and imparting to the spectrally resolved wavefront a prescribed two-dimensional phase distribution, one can change the tilt angle that we had in the previous slide. I can change the tilt of this plane intersecting with the light cone by changing the SLM phase, and as a result, this angle will be called the spectral tilt angle, and as a result, we are able to change the properties of these wave packets in free space. Two examples that we published a couple of years ago. One is starting to go to long distance propagation with these beams. We reached about 100 meters in the past. We have brand new results that we're carrying out at the TISTA facility on the Space Coast, where we reached now a kilometer propagation distance with 1 millimeter sized wave packets. We've also published in Nature Communications 2 years ago our demonstration of controlling the group velocity of the wave packet by changing that spectral tilt angle, and we demonstrated group velocities extending from half a C to 30 times C in free space, and negative group velocities extending back to -4 C. Once again, this does not violate relativistic causality. Special relativity does not apply to the group velocity, which is the velocity of the peak of a pulse. So no need for any justified fears there. So I'll give you one example of why it's interesting to change the group velocity of a wave packet in free space. So one application we just published late last year in Nature Communications is a demonstration of a free space delay line, which is a core component that will be required to construct all optical buffer for future communication networks. In the early 2000s until about 2010, people have been working on so-called slow light and fast light materials and structures that change the group velocity by changing the dispersion of some linear or nonlinear phenomenon, or constructing an optical device that exhibits a resonant behavior that allows for strong dispersion to change the group velocity. We propose to do this without any resonant structure, by changing the structure of the field itself. So we start off with two optical pulses in two different spectral windows, and they go through our setup, which is now segmented into multiple spectral channels, and in each channel we encode a particular spectral tilt angle, thereby changing the group velocity of that wave packet in free space. Now you can just let the wave packets travel, and they will then separate in free space temporally. And here's an example of data from that paper. And I like this figure a lot because I think it's the first time you see a result like this, where I start off with two pulses overlapping in space and time initially at z = 0. And as the two pulses travel in free space, they separate from each other because each one travels at a different group velocity. This tilted white line is the reference luminal pulse. This is where a pulse would be at different axial positions if we're traveling at z. One of the wave packets is superluminal, so it's ahead of it, and one is subluminal, so it's behind it. We are no longer limited by the delay bandwidth product that mod or work on slow light. We have actually the opposite limitation. So in slow light, because of the resonance nature of most of these effects, the bandwidth was limited. So even though there was a large delay, that delay was only applicable to long pulses. In our case, it's easy for us to delay short pulses. Femtosecond and picosecond pulses, quite straightforward. We struggle still with synthesizing nanosecond space-time wave packets. The level of picosecond pulses, we can delay these wave packets by about 100 times the pulse width. Now, this is at the level of propagation free space. So how would these wave packets interact with matter? And what I would like to convince you today is that we need to rethink all our rules of thumb in optics once the spatial and temporal degrees of freedom are associated with each other in a precise manner. Everything we know in textbook optics presumes implicitly that the spatial and temporal degrees of freedom are separable from each other. The temporal spectrum as a function of omega is separable from the spatial spectrum as a function of kx. So let's look at what would happen in the simplest possible form of interaction with matter: refraction of light at a planar interface between two non-dispersive transparent dielectrics, each described simply by a refractive index. Now, as you go from a medium refractive index N1 to a medium refractive index N2, the light cone opening angle is going to change. And this is why one of the reasons why I advocate for the visualization on the surface of the light cone. It's going to come in extremely handy here to explain why refraction space-time wave packets follow such different rules than we are used to. So starting with a monochromatic plane wave, that's, as we said, that's a point on the surface of the light cone. As you go to a higher refractive index medium, the light cone opening angle increases. The separation between points on the light cone increases. So what happens is something I call light cone inflation. Okay, that change in the light cone underlies Snell's law. So now what happens if you have a pulsed plane wave with a finite temporal bandwidth? Then it's represented on the light line initially. You go to a higher index medium, light cone inflation occurs. The separation between points increase as the opening angle increases. We have this invariant temporal bandwidth. The wavelengths don't change, but as a result of light cone inflation, the extent over the kz axis, the axial wave numbers inflate. And so the slope decreases, and hence the group velocity decreases in the second medium. As we expect, as you go from a low index or high index medium, we expect the pulses to slow down, even at normal incidence. Now, that is what we're used to. I want to then bring up a phenomenon that typically goes unnoticed. Think of now a monochromatic beam, a beam with finite spatial bandwidth incident normally on the interface. Normally, but because you have a finite spatial bandwidth, the beam size, there are underlying plane waves that are incident on the interface obliquely. Because we have a single wavelength, we're at the intersection of light cone with a plane, light cone inflation here, given the invariance of the spatial bandwidth, because the transverse wave number is invariant across a planar interface, given that the spatial bandwidth remains fixed, in this case, the axial bandwidth decreases, as opposed to the increase for a pulse plane wave. However, that goes unnoticed because for a monochromatic beam, we can't define a group velocity. But now think of our wave packets where we have finite temporal and spatial bandwidths. Those two phenomena will happen at the same time. We have competition between two effects, an increase in the axial wave numbers as a result of light cone inflation, when we go from low index to high index, and a decrease in the axial wave numbers as a result of the invariance of the spatial bandwidth. So according to which effect wins out, we can have a situation where the group velocity decreases as you go to a high index medium as naturally expected, or anomalously increases when you go to a high index medium. And it turns out one can derive a very simple law of refraction for our space-time wave packets. N1 and N2 are the refractive indices of the two materials. N1 tilde, N2 tilde are the group indices, the inverse of the group velocities in the two media. So you synthesize the space-time wave packet with group index N1 tilde in the first medium, and you monitor what happens to it as you go into the second medium. And even at normal incidence, we have a very intriguing relationship between the group indices, here represented by the spectral tilt angles. So increasing the spectral tilt angle increases the group velocity. Because of this curved nature, it intersects with the two diagonals. Now let's think what these diagonals are. The first diagonal, theta 1 equals theta 2, that represents a wave packet that traverses the interface while retaining its group velocity. Given that it intersects with this curve, that means that for any pair of media, no matter what the index contrast is, there is always a wave packet that can traverse the interface between the two media without changing group velocity. The intersection with the other diagonal represents a wave packet that traverses the interface while maintaining the magnitude of its group velocity but switching sign. In other words, group velocity inversion. We've demonstrated these phenomena by comparing the propagation of these wave packets in air and BK7 glass. And by changing and moving along that curve, we go from a situation of normal refraction, where the pulse is delayed in glass more than air, to a threshold configuration, where light travels in glass and air at the same group velocities, and a anomalous group velocity anomalous group velocity refraction. The pulse traverses glass faster than it traverses a layer of air at the same thickness. And then finally, we show here an example of group velocity inversion, where we have a wave packet traversing either magnesium fluoride or BK7 magnesium fluoride. As you know, the refractive index is much lower BK7. However, it emerges from it with the opposite sign of group delay. In other words, it has the same group velocity but opposite sign. All that is in the normal incidence regime. When we go to oblique incidence, the angle of incidence and refraction, which are related via Snell's law for the central wavelength, lead to a modification of that rule relating the group velocities in two medium, which allows the group velocity in the second medium to change without changing the group velocity in the first medium, but by simply changing the angle of incidence at the interface. that the change with respect to normal instance depends whether are you in the superluminal or subluminal regime, in which case the group velocity in the second medium either increases or decreases. The subluminal regime is the interesting one because in that case, the group velocity in the second medium can increase with angle, which can allow us to demonstrate some very intriguing effects. The first one that just got published in Optics Letters, something we call isochronous spacetime wave packets. In physics, one typically looks for invariance principles or minimal principles. In optics, we typically think of minimal principles. Light takes the minimal optical path length from point A to point B. In mechanics, people also look for isochronous configurations where particles reach from point A to point B in different paths but take the same amount of time. We don't have that in the optics of homogeneous media where where the delay is always proportional to the propagation distance. But in our case, because light changes its group velocity in going to the second medium based not only on the properties of the two media, but on the angle of incidence at the interface, one can arrange for configurations where a pulse of light traverses an optical medium at fixed delay independently of the angle of incidence. So at large angle incidence, obviously I go a longer distance in the same medium, but I can guarantee by adjusting the spectral tilt angle of the incident wave packet that such a pulse takes the same amount of delay independently of the distance traversed in the medium. And we've done that in media with refractive indices extending from 1.34 for magnesium fluoride all the way to 2.3, about 2.3 in zinc selenide. So it's a very ubiquitous effect. So that's at the level of going through a single medium. We then have thought about this configuration, which we just published theoretically last year in our Nature Photonics paper, or a configuration called blind synchronization. Now think of the source of the pulses in one medium, sending pulses to a host of clocks in the second medium, and we only constrain the clocks to be in the same depth on the medium, but we don't know where they're located, and we're just broadcasting our pulses. One can arrange for the delay taken from the source in the first medium to the source in the second to be fixed independent of the location of the clocks. Of course, with traditional pulses, clocks farther away will receive the pulses later. In our cases, broadcasting our pulses guarantees that all the clocks can be synchronized. And it hasn't been published yet, but we have our first data in this field showing fixed delay for receivers at different depths in the medium that we did experiment in was sapphire. So stay tuned for this new data coming out. So in general, the refraction of space-time wave packets already shows you that the fundamental characteristics of these pulse beams is quite distinct from traditional forms of pulse optical fields. A second example of the funny behavior of these wave packets is in the area of acceleration. Now, there's various forms. There's only, I think, to the best of my knowledge, there's only two ways of producing optical pulses that accelerate in optics. One is to use airy pulses in a dispersive media because of the mathematical form of the pulse in interaction with the dispersion of the medium. An airy pulse will have a axially varying group velocity in the medium. And the other is by phase modulating X waves. Matteo Clerici proposed this in 2008 and was quickly done by Peter Sari's group in 2009. And they showed that also X waves can accelerate in free space if you modulate them in an appropriate way. However, I want you to look at the numbers here. The changes in the group velocity that have been reported in the well-known paper by Dimitri Kousselidis and Frank Wise, 2010 in Nature Photonics, the group velocity change was 10 to the minus 4c over a distance of 75 centimeters. And in the case of the X waves, the group velocity changes for acceleration, deceleration on the order 10 to the minus 3 to 10 to the minus 5 over 20 centimeters. So we are talking about minuscule changes, very small group velocity, group index changes over the course of propagation, and very precise measurements are required to be able to discern that. We have found that because of the extreme level of control we can exercise over the group velocity, we can now also produce incredibly higher amounts of acceleration. Having two different space-time wave packets with two different spectral tilt angles result in two very different group velocities. So now, rather than synthesizing our wave packet such that it occupies only that 1D trajectory associated with a fixed group velocity, we intersect the light cone with a wedge-like structure whose two facets correspond to the spectral tilt angles associated with the initial and terminal group velocities desired. Now the representation is a two-dimensional patch on the light cone, resulting from the intersection of this volumetric wedge with the light cone surface. Now that wave packet will accelerate from that group velocity, that initial group velocity, to the terminal ones. And on the SLM, rather than the linear phase associated with each wavelength in order to create fixed group velocity wave packets, we put a chirped phase, chirping between the two spatial frequencies that we want associated with each one of these wavelengths. And with that, we have produced accelerating wave packets with changes in group velocity, accelerating or decelerating of about c over only 20 millimeters. So tremendous amount of acceleration equivalent to a light beam in the vicinity of a black hole. Now, one other limitation, all previous experiments and in this experiment, is that the acceleration produced was always constant. In other words, the group velocity changes linearly along the propagation axis. We have very recent, this hasn't been published yet, we've been able now to produce arbitrary axial acceleration profiles. Pulsars not that have a fixed group velocity, hence zero acceleration, or linearly changing group velocity, hence fixed acceleration, but now quadratically changing group velocity, hence linearly changing acceleration, cubic deceleration, and hence quadratic change in the acceleration, or even non-integer powers. So acceleration that goes with 1 over square root the distance. And even composite accelerations, a pulse that starts off at some initial group velocity, accelerates some terminal velocity, then switches the sign of acceleration and decelerates back to the original group velocity, and then moving on beyond that at any fixed terminal group velocity. So literally arbitrary control over the axial acceleration profile. Very excited about this. Now, we've talked about group velocity. That's the lowest order term in the dispersion expansion of a wave packet. The second order would be group velocity dispersion. Now, in free space, plane wave pulses do not undergo GVD. If you have a pulse beam, space-time coupling can occur, leading inadvertently to GVD. What we're going to look at here is now, with our level of versatile control over the spatial temporal spectrum, can we introduce GVD, group velocity dispersion, at will in free space? I'm not going to go too deep into this. We have a paper that just appeared in ACS Photonics showing that we can also get out absolutely arbitrary dispersion profiles, not only GVD, but higher order coefficients of any magnitude and sign and superpositions thereof. I want to focus here on only a single example, something called a V wave. So now, rather than intersecting the light cone with a plane whose projection on the KZ omega plane is a straight line, indicating absence of GVD and control of group velocity, but whose projection on KX omega is hence a parabola, I want to reverse that and instead intersect the light cone with a paraboloid of revolution such that its projection on the KX omega plane is a straight line. Unfortunately, the projection on KZ omega will not be a straight line, thus indicating group velocity dispersion occurring in free space. I want to focus on this linear relationship between KX and omega for a reason. If you look at the expansion of the axial wave number for a monochromatic beam propagating free space, where the quadratic term will be quadratic in kx, hence diffraction. And then I want to look at the expansion of the axial wave number for a plane wave pulse in a dispersive medium. The second order term will be quadratic in omega, representing dispersion. You can see there's a clear analogy here. So if I'm able to create a wave packet, an optical field in which the frequency is linear related to the spatial frequency, so omega and kx are linear related to each other, these two equations become satisfied simultaneously. The quadratic terms become the two different facets of the same phenomenon. In other words, a Jane, you think of as Jane, the two-faced Roman god, you have a Janus situation here. Two different things are happening at the same time. The beam will diffract and disperse, and here's the kicker, at the same rate. This is the unique optical field whose diffraction length and dispersion length are guaranteed to be equal because of the underlying physics of the wave, not by adjusting the GVD of a material to adjust the diffraction rate of a beam. No, the actual structure of the wave packet guarantees that it diffracts and disperses at the same rate. Now that's an interesting physics conclusion. It comes into play very interestingly in the Talbot effect. Now, for those of you who don't know, the Talbot effect was observed by Talbot in 1843, I believe. It's a basic wave interference phenomenon where if you have a beam whose transverse profile is periodic, it will initially diffract, but then reconstruct itself at periodic axial positions that we call the Talbot length. A spatial field that is periodic in the transverse direction means that its spatial bandwidth is discretized periodic. Okay. If it's a pulse beam, then rather than these delta functions, I will have these vertical extents, but nevertheless, the discretization along kx determines the Talbot distance. Separately, in the 80s and 90s of the 1900s, so 150 years later after Talbot, a temporal Talbot effect was discovered in analogy to it. Rather than diffraction in free space, in space, you have dispersion in a dispersive medium. And so if you have a pulse train, a periodic sequence of pulses, in other words, if your spectrum along omega is discretized periodically, and you have dispersion in the medium, then you will get a temporal Talbot effect. The pulses first disperse, but then reorganize themselves into the initial periodic pattern at fixed distances that we call the temporal Talbot length. The question I want to pose to you is, can one observe a spatio-temporal Talbot effect? Can one have a beam that has a space-time lattice structure, one that is periodic in time and periodic in space, so it has a space-time lattice that undergoes diffraction and dispersion, so you lose the lattice structure only for it to reorganize later on into the initial spatio-temporal lattice. Now one can imagine taking a pulse beam, discretizing it along both spatial and temporal frequencies, and then traveling in a dispersive media and adjusting the GVD coefficient such that the Talbot lengths in space and time are equal. That is conceivable theoretically, but I doubt it will ever be done experimentally for a very important reason. One second. The temporal Talbot effect has never been observed in a bulk medium, has only been observed in optical fibers. The reason is that dispersion and diffraction are independent effects in optics. They have very different length scales on which they manifest themselves. And given the dispersion coefficients we have in known media, you need a long distance to propagate in order for the Talbot effect to occur. And as a result, it has only been demonstrated in confined fields in optical fibers. So while theoretically this dispersive bulk phenomena may be one day conceivable, I highly doubt it. However, what we can do with space-time wave packets is the following. Using our V-wave structure, we now can control the amount of GVD observed in free space. We can control its magnitude to very large values so the dispersion length is small. And furthermore, this is the critical point, I don't need to adjust the diffraction and dispersive properties to match each other. By the very fact that the spectrum occupies a V shape, I am guaranteed that the diffraction and dispersive lengths are going to be equal. So if I have a continuous V-wave spectrum, I will see diffraction and dispersion. But if I discretize it, I will see a space-time lattice that undergoes the effect of diffraction and dispersion, only for it to revive later on and reconstruct into the initial lattice. And we observed this, and it's been published about a month ago in APL Photonics, the first observation of the Talbot effect in space and time simultaneously in any wave as a result of this underlying spatio-temporal spectral structure. So hopefully I've conveyed to you that the free space propagation of space-time wave packets follows very different rules than we are used to. I want to end quickly with a couple of examples of how the interaction of space-time wave packets with photonic devices bring new opportunities. So I'm going to look at two things: interaction of space-time wave packets with waveguides and with planar cavities. A waveguide confines light obviously in both transverse dimensions, and as a result in the spectral, the dispersion relationship, the relationship between the frequency and the axial wave number must be a one-dimensional trajectory. That should already ring a bell for you. Think of now an unpatented thin film. It's unpatented, so we don't have any of the losses associated with lithographically inscribing a structure in a substrate. Unfortunately, in a planar waveguide, although light is confined along this dimension by some guidance mechanism, index guiding, photonic crystal guiding, something like that, but it will diffract in the unconstrained direction, horizontal direction here. And that you can see clearly from the dispersion relationship that it's not a one-dimensional function, instead it's some two-dimensional patch. What we published in, this was a bit, I think, December last year in Nature Communications, is the first hybrid guided mode. It's a mode that's guided in a planar waveguide in one-dimensional by the conventional confinement, by a conventional confinement mechanism, but it's guided in the unconstrained dimension of the thin film by the space-time coupling that we introduce. As a result, we are back now to a one-dimensional dispersion relationship. But for the first time, these hybrid guided modes are completely free of dispersion. It's easy to show that. Any guided mode must be dispersive. It is impossible to create a GVD-free guided mode over a finite spectrum. You can have GVD 0 at one wavelength. You can flatten the GVD as much as you can in a nano waveguide by controlling the size and the index contrast, but it's impossible to have a guided mode with a absolutely linear relationship between omega and beta. In our case, we can do that with our approach. In other words, the space-time coupling we introduce in the unconstrained dimension can override the impact of the boundary conditions imposed on the field in the waveguide direction. And you can see that clearly by thinking of once again, the light cone. Each mode would have a light cone that differs from the free space light cone by the nature of the confinement mechanism in the waveguide structure. However, we will then intersect that modified light cone associated with the waveguide mode with a tilted plane, thereby identifying what is the one-to-one relationship between spatial and temporal frequencies needed to create a GVD-free mode. Furthermore, it's not only GVD. We override completely the boundary conditions imposed by the waveguide, and hence, besides being GVD free, the modal index is under our control. And we show that by changing the spectral tilt angle and be able to change the group index of the same fundamental mode of the waveguide at will. So this was published late last year. We have a paper ready for submission now where we have done this for a multimode waveguide and are able now to control the group index of the individual modes independently of the waveguide structure. So that gives you a flavor of how these type of fields will interact with waveguides. The final example is the interaction of space-time wave packets with a planar cavity. Now, on resonance, obviously a planar cavity will allow only a narrow spectrum to traverse the cavity as dictated by the resonance line width. So if I have a high Q cavity, an ultra short pulse entering it, the pulse will broaden in time and narrow in spectrum after you traverse. We can, by looking at the dispersion relationship of the cavity, and the cavity introduces a spatial temporal dispersion relationship. That'll be clear in a couple of slides. We then match that relationship and generate wave packets that can traverse the cavity without spectral filtering, even if the bandwidth far exceeds the resonant line width of the cavity. And we show here, for example, here's the cavity line width, the resonant line width of the cavity, and we can transmit through the cavity a much broader spectrum than the cavity line width, and hence also much smaller pulses. Now, cavities are critical in optics because you get resonant field buildup in the cavity, which you use to enhance optical effects, whether linear or nonlinear. And so, however, all these resonant buildup effects only occur over those narrow resonant spectra. This approach allows us now to harness the useful aspects, the useful enhancements, resonant enhancements over a broad continuous spectrum unconstrained by the resonant line width of the cavity. And one example I'll show you is in the area of solar energy. One could think of putting a thin film solar cell that absorbs weakly in the near infrared. One could put it in a cavity to enhance the near infrared absorption. The issue with, and in fact get 100% absorption using the effect known as CPA, coherent perfect absorption. Coherent perfect absorption indicates that if you put a thin, weakly absorbing layer in an appropriately designed cavity, you can guarantee 100% absorption. However, that occurs only on resonance. So what we're going to do here is combine CPA, coherent perfect absorption, along with omniresonance, coupling the spatial and temporal degrees of freedom of the incident sunlight, such that that resonant enhancement absorption is harnessed over a broad continuous spectrum. So that requires placing the thin film solar cell fabricating it within an optical cavity, and then introducing a light preconditioning system that enables the resonant enhancement to be harnessed over a broad bandwidth. This is the bare cell. It's a thin film, PIN amorphous silicon, PIN junction. Putting it just in the cavity results in emergence of a lot of resonances, including the infrared. And as you can see, the optical absorption here is close to 100%, even though the base absorption of the cavity is very small. So the material, the amorphous silicon, is very small in the infrared. We build this all using only planar deposition techniques. It's all done in the Harvard clean room in Cambridge. We first deposit a Bragg mirror as a back reflector. We then deposit the PIN layers, and then we have also a silica spacer that's placed at the top after carving out the connections for the amorphous silica cell, and then finally deposit a front mirror. This is what just appeared in advanced optical materials. We've since then been able to simplify the cavity structure a bit, but that's not ready for, those results not ready for prime time yet. But suffice it to say, we can get rid of the two mirrors now, the two dielectric Bragg mirrors, and replace them by metallic reflectors as in traditional cells. But in any case, here we have a silica spacer on top of the amorphous silicon cell, followed by a front Bragg mirror. This is the bare cell without the omniresonant structure. As you can see, we can measure the resonances very clearly within the band gap opened up by the two Bragg mirrors. And then by introducing our coupling between Kx and omega, our omniresonance structure, we can flatten out the resonances so that they are horizontal here, with the horizontal axis being lambda, so that the resonance is extending across a continuous regime. This is a level of optical measurements. We measure the optical absorption in the cell and see the enhancement and broadening of the resonance. We then measure the external quantum efficiency. We measure the electrical current produced in this unique configuration, and we see here a flattening of the resonant enhancement in the external quantum efficiency. And in the near infrared, over the spectrum extending from 660 to 740, where the absorption of amorphous silica drops, we get a doubling in the external quantum efficiency of the cell. Now, the preconditioning system has gone through a couple of iterations, and now at Purdue, a lot of groups are interested in metasurfaces. So those who work on that, I'd like them to think about this problem. Can a metasurface produce the angular dispersion required for this to happen, the specific relationship between Kx and lambda to occur? The first iteration of it, we used a grating. A grating can produce angular dispersion, but it has the wrong sign for planar carity and inadequate magnitude, but we fixed that with a lens. The problem with the lens, obviously, it's a bulk device, not going to be useful in the context of solar energy, and it requires alignment. We then were able to replace the lens with a second grating, but tilted with respect to the first. So now we're able to get the correct angular dispersion, but once again, because of the large angle here, that's going to be a bulky system if you think about a large area solar cell. The next iteration, we then replaced this tilt angle by a deflection by a prism, and now everything is alignment free. However, that large angle means a large prism, still bulky, and so in the final iteration, we've replaced that bulk prism by an array of micro prisms that deflected that angle. So now you have two gratings sandwiching an array of microprisms that give the preconditioning required for this omniresonant enhancement in solar energy. The question I'm posing to you guys, hopefully think about it, is can a single nanostructured or microstructured surface produce the requisite angular dispersion that you can see here, this association between wavelength and deflection angle? If so, that would have will have really tremendous impact. So with that, the current work we're doing, we're now coupling these into optical fibers. We're working on injecting them into an actual optical communication network type scenario. We're starting to look at nonlinear effects, application to light cone, light sheet microscopy, etc. So hopefully the message I've delivered today can be summarized in the following two conclusions. The work I would characterize as really two fields, space-time optics and space-time photonics. And the message boils down to coupling precisely the spatial and temporal degrees of freedom in pulsed optical beams results in new type of behavior in free space and new opportunities for new modalities of interaction with photonic devices. This is a very fast-moving field. We've had major epiphanies over the last 3-4 weeks. And so offline, I can give you a whole different picture now of how to understand what's actually going on underlying these events, these effects. But stay tuned, because this is a very rapidly moving field, and hopefully some of you guys are excited enough to join. So thank you very much for your attention.
Thank you, Professor, for the interesting talk. I will encourage the audience to unmute yourself, ask questions, or post them in the chat box. So meanwhile, I had a basic question that involved the diffraction-free setup that you had shown in the first half of the slides. So here I see that along one of the directions, it's the phase profile that's applied is going to help bring this correlation between frequency and spatial frequency. Now, for a more generic and arbitrary control of getting to anywhere or any profile in the light cone, does one have to also take this output beam and send it over through a grating cylindrical lens SLM that's perpendicularly aligned to the first set. So is that required, or is this enough for?
You're talking about two dimensions.
Yeah.
Two spatial dimensions. So that's an excellent question. The SLM here has two dimensions. One is taken up by wavelengths, and so the other modulates kx. So we're left with ky. What to do about ky? If you were to go through a similar setup rotated 90 degrees, you would also manipulate ky, but ky and kx would be independent of each other. That's not what you want. You want kr to be related to the omegas. In other words, how do I control the three-dimensional spectrum mapped by kx, ky, or spanned by kx, ky, and omega? So that's a very good question. It's a very difficult thing to do. Everything I've shown here today is with one-dimensional control in space, not two. We've recently finally succeeded in doing it, and interestingly, at the same time, Alan Wilner's group at USC has also cracked the code in a slightly different approach than ours. So we're trying to synchronize the publication of our two papers that hopefully we submit in a couple of weeks from now. It is not by a sequence of two SLMs. That's not going to work because, like I said, that still works in a Cartesian coordinate. So to give you, I don't want to say anything because it's not online yet and hasn't been published. But what you want to think about is how can an SLM produce a correlation between wavelength and a radial spatial frequency? So that's basically the setup that we have produced. One that uses SLM still, but that instead couples each wavelength to a single radial spatial frequency. So that's spatial transformation, that geometric transformation is the only missing ingredient here. It took us a while because, and this is an interesting comment about optics in general, with all the advances in nanophotonics, we've forgotten the basics of optics. And it turns out that people in the 70s had solved that problem. We just weren't aware of it. And so we revived that solution of how to do geometric transformations from Cartesian to polar coordinates.
Okay, thank you. Anybody else with questions?
I'm curious to hear from Andy specifically. I can see him.
Yeah, Ayman, thank you for an interesting and very provocative talk. A lot of interesting ideas packed into a short time. So I've got two questions that came to mind. One is also on the subject of diffraction-free beams.
Yes.
And I'm just wondering how you define that. I've never followed it this much, but I'm aware, for example, in some of the early work that you referred to briefly on Bessel beams.
Yes.
Maybe had to do with the main lobe, but there was a corollary as there was a large amount of energy in the wings that wasn't accounted for.
Correct.
Is that sort of still the story in when you talk about diffraction-free beams, or you define it in a different way?
Yeah, so the Bessel beam, because it was defined, it's a monochromatic beam, so the diffraction-free aspect is only the spatial one, and you nailed it right on the head. What the diffraction-free or the extended diffraction-free propagation distance compared to a Gaussian beam, for example, is related to comparing the propagation of the central lobe of the Bessel beam to the peak or to the center of a Gaussian beam. However, there's extensive amount of energy in the rings of the Bessel beam. And if you cut them, obviously you go back to regular diffraction. There's a second limitation here. One could say, well, I don't care about the energy in the secondary rings because all the energy, whether in the central peak or in the secondary rings, are being transported invariantly. So who cares what the energy distribution is transversely, as long as it travels invariantly forever. Now, if you think about the original proposal by Joe Eberle and Durnin, how to produce it, they start off with an annular ring, and then with a lens, they're able to produce the Bessel beam. Bessel beam is only produced if that annulus has infinitely small thickness, hence the need for infinite energy. In physically realizable situations, realistic situations, you have a finite thickness, and so there's a finite propagation distance for the Bessel beam. And so then you have to come up with some type of measure of the distance over which maybe the central peak drops by 50%. So that's how you define the diffraction distance for the Bessel beam. And then there's an element of subjectivity in how you compare it to a Gaussian beam. In our case, we have a pulse beam. So there's both a spatial extent and a temporal extent. The equivalent of the annulus is, in our case, something we call the spectral uncertainty. How carefully can you associate each frequency with each temporal frequency, each spatial frequency? In any finite system, there's going to be some finite spectral uncertainty. And it turns out the propagation distance, in our case, is governed by that spectral uncertainty. How carefully you can associate each kx with each omega. With that, the propagation distance can increase if you reduce it. So if you go to larger gratings, smaller, the better spectral resolution, you're able to increase considerably the propagation distance. Now, how do we compare it to a traditional beam? We follow basically the same route as the Bessel, but with an interesting result, an interesting contrast. Because of the different wavelengths entering into it, we don't have side lobes at t equals 0. It's all focused at the center. The side lobes appear at later and earlier t's, hence that X shape. That X shape basically is displacing the rings from the Bessel beam away from t equals 0. And so if you have a shutter that opens in space and time at the center, you will capture the peak of the pulse without any side lobes. But a camera that is slow, that integrates over time, will see a similar distribution of energy in the side lobes as a Bessel beam.
Good, thank you. My other one, and we touched maybe on it a little bit, was you mentioned sort of the size of the grating, or the spectral uncertainty. In my language, it said it relates to the spectral resolution.
Yes.
Of your setup, even as you would talk about with monochromator.
Yeah.
But I want to refer also to the work you referred to as an optical buffer, and to sort of look at similarities or differences compared to earlier work doing pulse shapers, which considered only the temporal behavior. Yeah. And so there, as I think that by putting a linear spectral phase onto the spectrum, you could sort of get a delay. I suspect with the same limits, that it's limited essentially by the inverse of the spectral resolution, how much delay you can get, and I suspect that's the case. So I suspect the main difference between that work is you showed an experiment where you had 2 input spots, and were able to put presumably different linear phases on the different spatial spots. So is it essentially the same analogy there, but now extended to sort of essentially independent delay control in the other transverse direction?
Yeah, so I haven't thought through this. This is a little tricky to think through. So if you put a linear phase spectrally, you can obviously introduce different total delays, right? The difference here is that the delay is occurring during propagation. I don't have a fixed total delay being produced. Instead, the delay is coming from the propagation over space here. Now, by changing the phase structure on the SLM, I can get, as I think mentioned earlier, I can get negative group velocities. So I can get the pulse to travel backwards with respect to these. I didn't put it's in the Nature Communications paper, but I didn't put the slide here. The pulse can actually travel back. There you get the laser pointer here. So here you can see, compared to this line, which is the luminal one is traveling ahead of it, one is behind it. Obviously, if you fix the plane, then you have a total group delay, and that might be mimicked by the SLM with only a linear phase along omega. I have to think through that. But the configuration that you cannot do that way is, and that the data for that shown in the paper, having the wave packet travel backwards like that, and hence first appear at a large z and then move backwards with time. That cannot be captured with the linear phase on the frequency. That requires a spatial degree of freedom. Now, is that useful in this context? I'm not sure, but that's a configuration, one of the configurations that cannot be captured by simply putting a phase on the SLM. I didn't put, there's a different type of presentation I give talking about these, because like you said, one could think, and you boiled it down to kind of its essence. I'm putting a phase on the SLM to modulate the wavefront in some way. Why would that lead to something unexpected compared to, for example, just using a grating? A grating introduces angular dispersion. An SLM has smaller spatial resolution than a grating, so unlikely that it's going to increase the angular dispersion. What can we do extra here besides deflecting each wavelength at a different angle? And so one of the things we've understood this year, and it might sound even more provocative, is that what an SLM in combination with a grating can do, if you modulate the SLM along both directions, not only along the frequency, is to introduce non-differentiable angular dispersion. Given that the SLM is able to manipulate each wavelength spatially independent of the others, each column is independent, the mathematical form of the deflection angle as a function of wavelength can be arbitrary. And in fact, underlying all of our beams is a square root omega dependence. That's the parabola that I talked about. As we know, square root omega at omega equals 0, omega is the difference between the carrier frequency, doesn't have a derivative. The derivative is not defined at omega equals 0. A grating, a prism, all conventional optical components can only produce differentiable angular dispersion. A grating plus an SLM can produce non-differentiable angular dispersion, which underlies all of this. And so that's why there are some configurations that emerge that one can do by modulating omega alone. But I'll leave it at that because these papers haven't come out yet.
Yeah, interesting. Last comment is, I haven't quite thought about it this way, but again, in the pulse shaper, the one spatial dimensions, certainly one way you can move the pulse essentially forward or backward in time compared to the non-modulated case.
Yeah.
And I've always understood that as essentially looking within the free space part of the pulse shaper, what path does the beam take between grating, lens, spatial light modulator, mask, and back. You putting a delay on it corresponds to actually physical deflection.
Yes.
And because of the grating tilt, that can actually take a longer or shorter path than it would have without the modulation.
Yes.
And so that part I thought of, part I hadn't thought of till this discussion, is maybe one connect, sort of the line of thinking I'm presenting with what you're presenting, is we were always interested in that, in sort of beam before the grating versus beam after the last grating. So we kind of take out any angular dispersion and just look at the one-dimensional time. So I think it might have some interesting relationship to what you're presenting on this slide. If you take a cut at a fixed propagation line.
You're absolutely right. But you just keep in mind that the angular dispersion in your configuration, which comes from the grating, will always be differentiable.
Yeah. No, I just sort of, again, trying to, connect these results. I think that helps.
Definitely.
I think I've taken way too much time in case there's other student questions. But again, thank you for presenting to our group.
Thank you. Like I said, a lot of this was inspired by your work, and many people look at this work and say, "This is Andy plus Fourier optics."
Well, wonderful.
Okay, if anybody else has questions, please unmute yourselves. You can also post it in the chat box. I guess if nobody is coming up with any questions, then I would like to thank our speaker, Professor Abouraddy, for this interesting presentation, and also for I thank you for accepting our invitation and giving this talk. And with that, I would like to conclude this event. Then, thank you, everyone.
Thank you, Suhaib. Thank you, guys.